Hello everyone. Today I stand before you to unravel the secrets of the finite element method, a powerful numerical technique that has revolutionized the world of engineering analysis. Welcome to this captivating journey into the realm of desyncretization process and the fascinating world of elements used in finite element method. What is finite element method? The finite element method is a powerful numerical technique used to solve complex engineering problems. It involves dividing the problem domain into smaller elements which are connected to each other from a mesh. The properties of these elements are then used to represent the behavior of the system under analysis. FEM has become an essential tool in many fields of engineering, including structural analysis, fluid dynamics, and heat transfer. It allows engineers to simulate the behavior of complex systems and predict their response to various loads and conditions without the need of expensive physical testing. The discretization process. The discretization process is a fundamental aspect of FEM. It involves dividing the problem domain into smaller elements, each with its own set of properties. These elements are then connected to each other to form a mesh, which represents the behavior of the system under analysis. The accuracy of the FEM solution depends on the size and shape of the elements used in the discretization process. Smaller elements provide more accurate results but require more computational resources, while larger elements may lead to inaccuracy in the solution. Importance of discretization. Discretization is a technique used in a finite element method to analyze complex geometries and structures. It divides the problem into smaller elements, allowing for all allowing for a localized solution that can be used to approximate the global behavior. Additionally, it converts the continuous problem into a discrete system of equations, making it amenable to numerical solution techniques. Types of elements used in FEM. There are several types of elements commonly used in FEM, including linear, quadratic, and higher order elements. Linear elements have straight edges and corners, while quadratic elements have curved edges and corners. The choice of element type depends on the complexity of the system under analysis and the accuracy required for the solution. Linear elements are simpler, and computationally less expensive but may not accurately represent systems with complex geometries or material properties. Quadratic and higher order elements provide more accurate results but require more computational resources. In addition to linear elements, there are several types of elements used in FEM. Quadratic elements have curved edges and allowing representation of complex geometries and material properties. However, they require more computational resources and linear elements. Cubic elements, which have even more curved edges and corners, are even more accurate but require even more computational resources. Another type of element is the shell element, which represents thin structures such as plates and shells. Shell elements can be either linear or non-linear and can accurately represent both small and large deformations. Finally, solid elements are used to represent three-dimensional objects and can accurately capture complex materials behavior such as plasticity and damage. However, they require the most computational resources of any element type. Linear elements. Linear elements are the simplest type of element used in FEM. They have straight edges and corners and are often used to represent simple geometries such as beams and trusses. Linear elements are computationally less expensive than other types of elements but may not accurately represent systems with complex geometries or material properties. One advantage of linear elements is that they are easy to use and require less computational resources, making them ideal for rapid prototyping and design iterations. However, their simplicity may lead to inaccuracies in the solution, especially for systems with non-linear behavior or large deformations. One-dimensional elements. Rod or ball elements represented by line segments. These elements are suitable for analyzing axial deformation and one-dimensional structures. Beam elements, modeled as line segments with additional rotational degrees of freedom. Beam elements are used for analyzing bending and torsional behaviors. Two-dimensional elements. Triangular elements formed by connecting three nodes. Triangular elements are widely used due to their simplicity and flexibility in handling complex geometries. Quadrilateral elements. Constructed using four nodes, and quadrilateral elements provide better representation of rectangular or square shaped structures. Three dimensional elements. Tetrahedral elements composed of four nodes. Tetrahedral elements are suitable for analyzing irregularly shaped 3D structures such as fluid flow or stress distributed in solids. Hexahedral elements, represented by 8 nodes. Hexahedral elements are commonly used for cubic or rectangular geometries in structure analysis. Quadratic elements are more complex types of element used in FEM. They have curved edges and corners and are often used to represent systems and complex geometries or material properties. Quadratic elements provide more accurate results than linear elements but require more computational resources. One advantage of quadratic elements is that they can accurately represent systems with non-linear behavior or large deformations. However, their complexity may make them difficult to use, especially for rapid prototyping and design iterations. Conclusion. In conclusion, the finite element method is a very powerful numerical technique used to solve complex engineering problems. The discretization process, which involves dividing the problem domain into smaller elements, plays a crucial role in accurately representing the behavior of system under analysis. The choice of element type depends on the complexity of the system under analysis and the accuracy required for the solution. Linear elements are simpler and computationally less expensive but may not accurately represent systems with complex geometries or material properties. Quadratic and higher order elements provide more accurate results but require more computational resources. By selecting appropriate elements and using the right discretization technique, engineers can simulate the behavior of complex systems and predict the response of various loads and conditions.